Welcome to the Sci-GaIA Winter School for Application Development. My name is Bruce Becker, as you've seen in the introductory video, and I'm going to be talking about the prerequisites for this course, the things that you'll need and the tools that you'll need to be able to take part in the course. So, let's jump right into it. There are a couple of things which we need to get out of the way before you start taking this course. Some theory, some philosophy, a little bit of practical tools. So we're going to be covering the following aspects. A lot of considerations before you start. We're going to be working together at a distance, so we're not going to be physically in the same place. And so there is a certain way in which we need to work together, which we'd like to cover in this prerequisites. We'll be talking a little bit about the philosophy and practice of continuous integration, which is a core component of this course and which will be used all throughout the course. I'll be speaking about the tools that you'll need, and we'll go quite into detail with some practical tasks for two of the specific tools, those being GitHub and Docker. So let's get into it. Some things to get us started. So first of all, by attending this course, this is just the beginning of a project that you will be working on, and we expect that during the course of the course you do some work and you get to a certain state where things are working, but that after the course the work will carry on and the project won't die. So you should think about the future. You will not be working alone. The course applications have all been submitted, as you know, as teams. So already within a team you need to work together, but you also need to be able to collaborate effectively with the lecturers. Things will always go wrong. So we know this from our experience, and whoever says that things don't go wrong needs to come back to Earth because they've been living on a different planet until now. Things always go wrong, and so we need to take that into consideration and plan our way of working to take that into account. Another thing to remember is that if something is worth doing, it's worth keeping. That means that we should try to avoid bad habits which allow us to throw away work and instead put a little bit of extra efforts into working in a way which is conducive to keeping our work. If you haven't expressed it, it doesn't exist. And that refers to the fact that when you do something, usually it needs to be written down in a change-controlled environment. If you do ephemeral work like typing commands on the keyboard or browsing the web to find information and reading, that's all part of the process, but it can't be recalled and it can't be shown effectively to other people. So if you haven't written it in something that's persistent, whether that be a file or a database or something else, then essentially it doesn't exist. Another aspect to keep in mind is that if you can't reproduce something, if you can't show an effect or action again to somebody else, and more importantly, if they can't do it on your behalf, then it also doesn't exist. It's just your opinion or your strange anecdotal evidence. And of course, these things happen all the time, but we should give more weight to those things which we can reproduce. And so we should be able to do things in a way which are reproducible. The next thing to keep in mind is that if you haven't tested it, whatever that is, it also doesn't exist. That means that it probably is not going to work, and you can't convince anybody who is working with you, be that your teammate or the staff in this case, that what you've done is correct. So these considerations are general considerations that anybody who works in the IT environment or science indeed needs to take into account. The final thing I want to put on the table before we get going is that people working and taking this course are going to be humans, I hope. So as a human, you should use your human abilities to the best of their capabilities. You don't want to be doing things that are better left to a machine. And in fact, we're going to be trying to automate as many of the tasks as we can in the school. So you should leave your time, which is very valuable and important, to the things which are best for humans, which is writing code and not necessarily checking and things like that. Those things will be automated and they will be taken care of by responsible robots, which we'll talk about in a little bit. So there are some things to keep in mind. Whatever you do today and during this course is probably going to be different in 1 or 2 years or even a few months' time. Your computer will be different, you'll be using a different laptop or maybe some other machine. You may not even be at the same institute. So you should do things in a way in which you're sure that you're going to have access to them, or somebody else is going to have access to them in 1 or 2 years or in the future at some point. During this course, we're going to have, obviously, a burst of activity. You're going to be working, hopefully, quite a lot during almost every day. And so you'll have a very good contextual understanding of what you're doing, because it'll be fresh in your mind. But just imagine that when the school finishes, you may have to go back to revisit the code or the work that you've done, and it can be quite difficult to understand what you've been doing. So it's a good idea to keep notes inside the code or the documents that you write, to make sure that you remind yourself, or whoever comes after you, why and what you've done. So lastly, just as a general consideration, be conscious of the fact that the future you is not going to be the same as the current you. You will know different things, you will forget some things. Try to keep all of this in mind when writing your code, because you'll thank yourself later. So that's taking care of the future. Now, you will be working with other people. And so the code that you write should be readable and understandable by other people. Now, that can be very tricky, because people speak different languages. They may have different contextual understanding or semantic understanding of the words that you use. For example, if someone writes a comment in English, that's quite different to writing a comment, the same comment, in French or Arabic. We don't expect you to write comments for all particular cases, but the most probable use that you think they will have in the future. Obviously, not with too much of an overhead. Right, so bear in mind that during the course, you will not be the only people reading this code. It's very easy to write the code, but actually reading code as a human is very difficult if you didn't write the code yourself. But you have to be conscious of that fact. The teachers, the staff, and your fellow teammates will have to read all of the code that you read. So writing human readable comments is a very important aspect of what we're doing. Secondly, it may not be automatic that you write code correctly the first time, no matter if it's a question of implementation, a particular algorithm, or so on. So it's a good idea to start with the practice of code review. We'll see how to use GitHub to do that, and we'll see how we're using automated testing to check whether or not your ideas are good. So the next consideration that we had was things will go terribly wrong, and that is a universal truth. This is more about an attitude towards writing code. So it doesn't pay off, in this case, to be optimistic about the environment in which your code will execute. You should be more defensive about that. You should not assume as much as you usually assume about the environment in which your code executes. That has certain implications for how you write code, and certain implications for the testing and so on that you include in the applications that you write. As a general rule, you should think that the more you assume about the environment in which your code will execute, the more probability there is that you will have errors or bugs. So obviously this is a trade-off between how much effort you put into making robust code and how much time you have available to write your applications. Finally, just remember that you cannot be trusted. You are a human being, you are prone to failure, but don't worry, we've got some automation to check your back. The next consideration that we had was, if it hasn't been expressed, it doesn't exist. So there's a great temptation usually to experiment, to get into a console, to try things. You may think that your application is just there, maybe a little bit of configuration needs to be done, and it'll be working. If these changes are made in an ephemeral way, in other words, on the console, by writing things on the terminal, or by checking things online, they will be lost as soon as you arrive at your working state, and even though things may be working, they may not stay that way, and you will forget how you got there. So the most important thing to do is to remember how you arrived at a working state, and not necessarily what was needed to do. In any case, whatever you do has to be written in some persistent way. So we'll leave this as an open issue. We suggest that you use some kind of automation tool to reproduce the work that you're doing. And this obviously depends on your application. We will be discussing this during the course on a case-by-case basis. The next consideration was, if you can't reproduce it, it doesn't exist. So this refers to bugs that may arise, particular pathological states of the application that it's doing something, you don't know what it is. The reproducibility of these states, these things that you need to address, is crucial. Something can't just be referred to in an anecdotal way or by describing it. It must be explicitly shown to exist or occur in a particular state. So, leaving aside the pathological cases, even the correct working state of the application needs to be reproducible. Right. So that means that when you pass the application, a final binary, or in this case, usually the WAR, Java WAR that you produce in your code, that is not sufficient. We need to know how that binary or that Java application was created, even if it's working, so that we can show that it is reproducible in different environments, under different conditions, and so on. Most of this will be covered by the automated testing, which is the responsibility of the school lecturers. So we hope to cover your back again on that. The next consideration was, if you haven't tested it, it doesn't work. This is an assumption that you should make about your code. So if your portlet, or if your application, or if your whatever it is you're working on has some kind of functionality, and you assume something about that functionality, you should test it. You should write a test either inside the application or in the testing environment, which tries to execute that functionality, which tries to see whether or not your assumption is correct. These tests will become hopefully more and more explicit as your application grows in complexity or grows in size. And again, some of them will make sense to have them within the application. Some of them will be done. This may seem like a lot of work to do for a simple application, but we'd like you to keep in mind the following. So if you don't enable some kind of automated code integration, continuous integration, automated testing, automated deployment, all of these things which seem like a lot of effort for very little payoff. If your application is very simple, it may seem like that. If the cost for not doing something like that is something that's referred to as technical debt. So you may go down a development path which leaves out automation completely and doesn't do any testing, and you just kind of assume that since it's so simple, it'll work. Well, as that application grows in size and complexity, you will involve more and more avenues for failure. And so the debt required to pay back to get to a working state if something breaks becomes bigger and bigger. It's better to pay this price, so to speak, in the beginning of the project. And so most of what we'll see in this prerequisites presentation shows you about setting up that environment which is conducive to testing. Right, and that environment will help you to avoid some of what we call the anti-patterns of software development. Those are bad habits or bad structures, bad algorithms for writing your code. They are easy to fall into. They are, in some cases, even subconscious. But please follow the link in the slides to see some of these anti-patterns and how we try to avoid them. Okay, so that's the kind of philosophy of how we expect you to start working in this winter school. One aspect which we need to cover is that of continuous integration, because this will be part of the testing for your work. Whenever you write code and you try to do one of the tutorials or submit a test for a new version of your application, it will be automatically tested by a service which we provide. Let's go a little bit into the theory and practice of continuous integration. So when working as a team, you basically want to work as independently but also as smoothly as possible. It's no use, if your team is made up of 5 people, for example, that all those 5 people work completely independently. Because at some point, you're going to have to merge your work and build one product. Otherwise, you'll end up with 5 products and a lot of repetition of functionality, code, problems, and so on. So continuous integration is a software development paradigm which is aimed at easing this problem, making people work independently, but also build software in a coherent way by eliminating the possibility, where possible, for introducing errors. So continuous integration allows you to be aware of the end result that any particular change of any of your team may make. That atomic change to the code base, what effect will that have on the final product? Continuous integration also allows you to ensure that there is an explicit expression of any errors that arrive. So a change in a code base will be directly linked to a particular error or positive state, depending. And continuous integration will also allow you to explicitly run those checks which you define to check whether your application is sane, if it's passing sanity checks, if it's passing functional checks, and if it will run in lots of different environments which you may expect it to run in. Okay, let's look at some of the best practices of continuous integration. These were taken from the links you see in the slide, and one of the foremost experts, and in fact one of the inventors of the philosophy of continuous integration, Martin Fowler, who works or used to work for ThoughtWorks, has got a very good overview of the best practices of continuous integration. So I'm just going to have the list of them here, and we'll go through them. First of all, maintain a code repository. That's kind of a no-brainer. Second of all, you need to automate the build. So no humans must be responsible for pushing the button that compiles the code. The build should be self-testing, so you shouldn't try to build something without it testing itself. Everyone who's working on the project should commit to the baseline, whether that be a particular branch or repository, every single day if they're working on it. So no work should be kept in a private environment and then put in en masse at some point. Every commit to the baseline, whether that be a branch or a repository, should be built. So you don't accumulate particular commits that may have introduced errors and you won't be sure where they are. Try to keep the build as fast as possible, because people will try to be agile in their software development, submitting many commits in small pieces, and if they have to wait maybe the whole day or a couple of hours, then that will slow down their development process. You want to test the build in a clone that looks just like the production environment. So we'll be using Docker for this particular purpose. But if you think that your application will be deployed in a particular environment, you need to simulate that environment or various environments which iterate on that, so that you can see what the particular effect of a change or a new version would be. Always make it easy to get the latest executables or deliverables. So these may be the WAR of your Java application, it may be a binary application, it may be a website that's been built, it may be anything that is the outcome of your build process. Make those easy to obtain, and in fact we'll be using a tool called Jenkins to be able to publish these things. But you could think about just storing it somewhere on a particular place, either on your repository or a web server or something else. Make sure that everybody in the team can see all of the builds. So not only the software developer, but the quality assurance person, the end user, and so on. Everybody should be able to look at the same code, the same results of the build. In our case, the students and the teachers should have access to all of the build results, the build artifacts, to be able to check where, which piece of code has created which error and whether or not the task that has been assigned to the students has actually been properly executed. And then finally, once you're sure that this is a mature application and it can be put into a production environment, automate that. Don't leave it up to some human who has to manually take this piece of application and put it into the production environment to have it available to your users. If you have done the best practice of continuous integration, you will have a fully functional, tested, reliable application which can be deployed automatically into the end environment. So that's that for the theory of continuous integration. That may sound like a lot of hot air for someone who's heard it for the first time, but actually it's quite easy to implement. And so what we're going to go into in the next part of this presentation is how we've gone and implemented these tools for the actual course. So the first one, maintain a repository. Well, that's easy. We'll be, in fact, forcing you as part of the tasks of this part of the course to create a change control repository with Git in GitHub. And so, that's kind of the easy bit. But the other bits, so how do you automate the testing? How do you run this testing in a clone of the production environment? We'll be showing you how to do these things with the tools that we've decided for this course in the next couple of slides. So just remember, in this course, there's various teams of students who are working on the application, but there's also a team of lecturers, and in fact, there's even a team of robots, which are all participating to deliver this course. And so you're not alone out there. In fact, courses usually have only the two sides. So you have the students, which are you, and the lecturers, which are us. But in this case, we've got actually a bunch of unsleeping drones, robots, software agents, call them what you like, which are going to tirelessly act on whatever it is that you're doing. So we'll see how they do that. So let's talk a little bit about how to implement some of the best practices in terms of automation, verification, and transparency. Remember, some of the best practices that we said, everybody should be able to see the same artifacts, everybody should be able to have access to the code and so on, right? How do we do this? So continuous integration services are going to be deployed for this course. In fact, they are being done as we speak. And they are being done with the same tools which we use to build the infrastructure services which these applications will be running on. I'm going to just refer to two of them. You're never going to actually use these particular tools because we, as the lecturers, are the ones who are doing this. But again, the creation of the services that we're using is all kind of open source and transparent. And if you want to see how it's done, then you can just go to the relevant repository and see the code that's in there. So the one thing we want to refer to is the tool called Ansible, which is the way in which we orchestrate these services. And one of these services is, in fact, Jenkins, which is a continuous integration platform based in Java. These are the two. The Jenkins in particular is the continuous integration environment, which has been delivered by Ansible. Right. How does this whole thing work? So basically, if you look at slide number 16, you'll see that you, the scientist or the students on the left-hand side, essentially write code. That's all you really have to do. You write code which gets committed to a GitHub repository. Jenkins listens to that. So whatever changes you make, Jenkins will take some action. And in fact, this action is quite complex. First, there's going to be provisioning an environment in which to execute your code. So you'll have to build your application, you may have to bring in some extra libraries, whatever that is, Jenkins will do that for you. Then Jenkins will execute some predefined tests. Those are to check whether your application will run in the production environment. Remember those best practices of continuous integration we spoke about. If any of these tests fail, then the result of the failure, including the console output and the particular change that created this failure, will be stored for the teacher and the students to be able to confer about. So you'll be able to refer to a particular hash or GitHub commit and say, this hash caused this error, please help me to resolve this issue. Vice versa, if you have a task to do, the lecturer can see exactly which part of your code is making the test which checks the task pass. And so we'll know when you've finished the task by the fact that your Jenkins tests are green. All of these underlying services, as we said, are provisioned by Ansible. And so if we need to change them during the course, it's very easy to do that. Okay, if you've passed the initial training and you've done all of the exercises, you're going to start working on the final application. This itself will be using Jenkins to run the integration tests. And in that case, we'll be staging the application to a Science Gateway environment, which looks exactly like the production environment. In fact, some of the functional tests will be the attempted submission of jobs in a computing case, or the interaction with various APIs that you may need for your application to work. So that is what you see on the final, the right-hand side, coming out of the blue integration environment. And that's where the students and the staff interact based on this automated environment. Right, so we've covered some basic philosophical principles, some good ways of getting started in writing your code, working in a way that's conducive to collaboration and conducive to future-proofing your work. That means that you're going to be working on something that's not just going to be thrown away at the end of this course. What we're going to be doing now is going into some technical detail about the tools which you'll be using on a day-to-day basis to actually get this course done. You may have experience with these tools. If you do, please follow the video lecture anyway, because some of the tasks that you'll have to do when following the courseware on OpenEdX, you'll have to see exactly which tasks there are in these slides. So, some of the tools which you will need to get started are essentially, the first important tool is a development machine. You'll need something to type on. That can be whatever you want. We suggest that this is a Linux machine. If you are using a Windows or an Apple machine, your mileage may vary with the content in this course, but you will be able to do all of the tasks that we ask you to. You may, however, not see the particular information about how to get started. Maybe there'll be some documentation links missing, because most of the documentation and links that we use in our slides refer to a Linux-based environment. If you have any problems, open a topic for discussion on the discussion forum. So having a machine to work on and an operating system which you are comfortable with, the next thing that you need is to understand very well a shell, and we suggest the bash shell. So some shell which works in a Linux environment, you will need to know how to program in that shell, because eventually you're going to have to write 1 or 2 bash scripts. Okay. Then you'll need an editor which you're comfortable with. We suggest Atom from GitHub. It's a very good, very powerful editor, but you can use any IDE which is relevant for your application. We're going to be showing you and asking you to do a couple of tasks using GitHub, the service, web service GitHub, and the web service Docker, and Docker Hub in particular, to get you started in the environment which you're going to be needing to both execute the tasks and tutorials for this course, as well as your actual project. So before we do that, let's just say what's not covered, particularly in these slides, in which we kind of assume that you have knowledge of. We assume that you have knowledge of working in the bash shell and writing bash scripts. If you don't, we have a link here to some very good training material by the Software Carpentry Foundation, which, if you follow, should bring you up to speed for the things that you need to follow the rest of the course. So if you feel that your skills in bash are a little bit lacking, take a moment and follow the tutorial or the training that the Software Carpentry Foundation provides. In fact, we'll be using a lot of the Software Carpentry Foundation material for Git, and so you may want to follow all of the initial courses for. So, the first service or tool that you'll absolutely need to be able to do this course is GitHub. Well, let's go into how we're going to be using GitHub and why. So GitHub should need no introduction. It's a very famous hosted Git service on the web, which anybody can use. But there are a couple of reasons why we've chosen to use this for this particular course. In fact, we could have chosen any kind of hosted or any kind of version control system for that matter, but we liked to use GitHub because of the following reasons. First of all, it's got a very nice to use user interface, quite intuitive, very clean, and so on. It's also a de facto social network of developers. So using GitHub puts you in the environments in which many other developers are already, and you will be able to collaborate easier with your peers as well as your teammates by using GitHub. We'll be making quite extensive usage of the GitHub API. This will usually happen behind the scenes, but the GitHub API is extremely functional and rich. So this is another reason why we've chosen to use GitHub. Finally, GitHub has very good relationships with academic institutes and academic activities, giving lots of free support to projects like ours. And so we suggest using this for research activities where you may need it. So let's dive into the first practical, the first tutorial that you have to do as part of this course. And that's very simple. That is just getting Git installed and set up on your machine. So the tasks that you have set before you are to install Git. If you have a Linux machine, you can see the first 2 lines of the slide tell you the commands that you need to run with escalation privileges, obviously, in a Debian or in a RPM environment. For any other operating system, be that Windows, Mac, or any other version of Linux, you can see the link there and see how to install Git on your development machine. So once you've done that, come back and we'll carry on. Right, so now you've got Git installed on your development machine and you can start using it. The first task that you have set up before you is the configuration of Git personally. So there's a full video of how to do this on YouTube in the link below there, but you need to follow the link under the title of this slide. That is the second lesson of the software carpentry Git lesson, which shows you how to configure Git. The next thing we want to talk a little bit about is something which is called Git Flow. So Git Flow is a kind of de facto standard for collaborating with repositories. And I forgot the link here, but it's going to come soon. So you need to read the link on the slides, which is definitely going to be there. You need to read the link on the slides and have a little bit of understanding about the way in which we expect people to work with Git. Because it's such a powerful tool and you can do almost anything you want in terms of change control with Git, this can make it very confusing for new users. So GitHub Flow is the kind of best practice which has evolved around many years of many people working with the tool and collaborating with each other, and this is kind of one of the best ways of clearly and cleanly collaborating with many different repositories. So GitHub Flow inherently includes many of the concepts which we've referred to in our previous slides, which are directly related to continuous integration or software quality assurance, such as testing and automation and so on. And you can find out more of the information in the link to GitHub Flow that you see on the slide. So it's time for the next practical, and that is to read the GitHub Flow article, make sure you understand it. If you have any questions, feel free to open a topic on the discussion forum around that. Familiarize yourself with the terminology of Git Flow, understand what a branch, what a pull request, what discussion means, all of these terms, and see how they work in the GitHub environment. If you really want, you can watch the further training videos that GitHub has provided at the following link just below. Right. So the next part of this GitHub practical is to create your GitHub account. If you already have a GitHub account, to be able to do this, we just need your GitHub username. If you don't have a GitHub account, you can follow the rest of these slides. So we'll show you the various aspects of GitHub and where important information is. In this case, we're talking about the dashboard, your personal profile, and your account settings. These are links which you'll need to remember and to understand where to get the relevant information, such as OAuth applications, SSH keys, and so on. So the GitHub dashboard is just your signed in github.com. If you go to github.com and you're signed in, on the top right corner, you should have a little picture with your profile. Maybe it's an auto-generated one if you don't have a picture of yourself. And that will take you to the various other parts of GitHub. The next thing we want to look at is your profile. So that is what we call the username after github.com. In my case, it's Brucelino. So github.com/Brucelino will take you to my profile, and there you'll see all of my contributions, which I've made to various repositories, and my activity over the past year. Everybody's dashboard will look a little bit different. Everybody's profile will also look a little bit different, but yours should have something that looks like what you see on slide 27. Finally, take a look at your profile settings. So this is under github.com/settings/profile. Take a look at, for example, your account profile and your SSH keys. You may want to add your own SSH keys to GitHub, which will be used by your Git clients when committing or retrieving your code. Also take a look at the various OAuth applications. These are applications which have been authorized by GitHub to read personal information about you. Right, so once you've done these three things, that is, have a look at your personal profile after you've created your account and your settings with the various information in there, we can move on to the next part of the GitHub tutorial. So, the next part of the GitHub practical is to create your first repository. For this, we're going to be using the software carpentry lesson plan again. In fact, in this case, we're using the third lesson of the software carpentry Git lesson. So, please go to the software carpentry lesson and create the repository as mentioned in that lesson in your GitHub, in your local machine. Once you've created that repository using git init and you've added it to your profile, I want you to make some changes to that repository. The changes that we expect to be made are described in the fourth lesson of the software carpentry Git lesson. Essentially, you need to add 1 or 2 files, commit them, and move on to the next stage. The next stage is creating what's called a remote. So far we've only been working on our laptops doing things with Git. What we want to do is push the changes in the repository that we've made to GitHub itself. To do this, you can follow the 7th lesson of the software carpentry Git lesson plan, and that is essentially creating the remote repository on GitHub and then pushing your changes from your laptop to GitHub. Once you have finished these practicals, these tutorials with Git, you should feel a little bit more comfortable about using Git itself and GitHub, both on the web interface and directly from your laptop. If you feel adventurous, try to play around with Git by making changes, working with your teammates, sending them pull requests, discussing, and so on. That's left up to you. And again, if you have any questions or ideas, please open a topic on the discussion forum. We're going to be moving on now to the second tool, which is essential for following this course, and that is the tool called Docker. So to get us involved, get us started using Docker, we need to go a little bit into the functionality and to get us started in using Docker, we need to understand a little bit about Linux containers themselves and how Docker implements these. So Linux containers will not be covered in depth in this course. You can read as much as you want on the web about the theory and practice of Linux containers, but we have chosen to use them because they're very good tools for development. In fact, we'll be using Linux containers to run most of the automated testing. It's a very lightweight and quick way of deploying applications in a testing environment compared to full-blown virtual machines. So we'll be using Docker to prepare a development environment which can be shared amongst the students. We'll be using Docker to test whatever work the students are doing in this predefined environment, and in fact there may be more than one of them. And we'll be using Docker containers, Linux containers, to validate the work that you do in various scenarios. So remember that containers are not virtual machines. We'll be using both of them, and you should decide when is the right time to use either. But the fundamental difference between a Linux container and a virtual machine is that you don't have access to the guest operating system in a Linux container. What you essentially have is a version-controlled process management system. So your application will have the same ideas applied to it as your code. That is, every change in your code will have a change in the application state, and these changes can be linked together and tested independently. So that is the most important aspect that we need to remember about why we're using Docker containers to test and deploy our applications. Right, so let's move on into the practicals which we have associated with Docker to get you up and running and ready to follow the rest of the course. The first practical is to install Docker. So what we mean by installing Docker in this case is actually the Docker engine. This is one component of the full Docker stack, which you can see more information about on their websites. But you will be needing Docker engine to run containers and make changes to them on your laptop. Once you've done that, we are going to have, we're going to need access to Docker Hub. Docker Hub is a place to publish and share applications, and application containers. So think of Docker Hub as a GitHub for applications, where GitHub is a place to share and collaborate on code. Docker Hub is a place to share and collaborate on actual applications contained inside the relevant containers. So with Docker Hub, we can easily reference individual containers, in fact, individual states of containers. We can keep version control of containers, making sure that there's a life cycle. And we can fork other people's work and rework or contribute to existing work inside the Docker containers. Right. Docker Hub is also a good way to ensure that your applications are always available, whether they need to be deployed in our testing environments or in some other production environments. They can always be pulled down from the centralized environment called Docker Hub. What we will be doing next is creating an account on Docker Hub and then working with the basic workflow of how to create, run, change and commit changes to Docker containers. So for the next practical, we will be creating our account on Docker Hub. As in the case of GitHub, if you already have an account on Docker Hub, all we need you to do to pass the test is to provide us with the username of your account on Docker Hub. If you haven't done that, go to hub.docker.com and sign up. You will need to provide a username, an email address, and set a password, and it's as simple as that. For the next practical, we want to create a repository for a Docker container which we will be working on. So before we do that, on our laptops, we want to perform a couple of basic tasks to make sure that our installation of Docker is working. The first task that we have to do is to, from the command line of our laptop, do a Docker login. This will use the Docker API on the command line to interact with Docker Hub. Remember, Docker Hub is where we will pull down the relevant images and containers for the work that we'll have to do, as well as store our own work eventually. So the first task is to log into Docker Hub. This can be done by simply typing Docker login and passing the username and password which you've created on Docker Hub. The next task, to see whether your Docker installation is working properly, is to run hello world. Simply type docker run hello world. Docker should pull down the hello world container from Docker Hub and give you some information on the command line. Finally, hello world is not a very useful application. It just simply says, hi, everything is working. Let's pull down something that's a little bit more familiar, and so we're going to be pulling down an Ubuntu Docker container. Simply type docker pull Ubuntu. That will stage locally to your laptop a container which has inside it a working Ubuntu image. Right, so let's move on to the next part of the tutorial. For this part, we'll expect you to start writing a little bit of code. In this case, it's a Docker file. To understand why we have to write things in a particular format or what Docker files are, you can read the quick starts of Docker Engine, which is linked on slide 37. So what we're going to be doing for this practical is using the work which you did for the GitHub practical, where you created your first repository with planets in it, and we're going to be including that in our first Docker container. To be able to do that, we need to start from a particular point. There's no use in starting from scratch. So we're going to be starting referencing a pre-configured container, in this case one provided by Ubuntu, with the tag 1510, that is Ubuntu 1510. That's what the first line says. Then we're going to be running some commands inside this container to update the container itself. In this case, we'll be installing Git, which we'll need to pull down our repository, and some compilers. Then we clone our repository locally. You need to include your own username and the particular URL to your first repository, which you did in the GitHub tutorial. So you clone your GitHub repository, and then to prove that everything is working, the check that we're going to be running is to see that you can access one of the files which has been cloned from your repository in the container. This may change based on what your file or repository is particularly called, so edit what you see on slide 38 accordingly. Right, the next task that we have assigned for the Docker parts is obviously got to do with making automated builds. Previously, when we had a Docker file, we needed to manually, on our laptop, build and check the container to see whether or not it was running. This runs counter to the philosophy that we described in the beginning about doing as little as possible. So Docker Hub provides us with the possibility to keep our Docker file in change control in a GitHub repository and link that directly to Docker Hub that will automatically build and deploy our new container every time a change is pushed to GitHub. That saves us from the manual task of having to do these things on our laptop and push them manually to Docker Hub. So for this practical, you will need to have a new repository with a Docker file in it and connect this repository from GitHub to Docker Hub. First thing we need to do is to create the new automated build on Docker Hub. So what you see on slide 40 is your profile on Docker Hub, simply going to hub.docker.com. On the top right-hand corner, you can click on Create and select Automated Build. What you should see is an option of connecting this Docker Hub repository to either a GitHub repository or a Bitbucket repository. These are the two integrations which Docker Hub has currently. We'll be using the GitHub integration, so you click on that. Then you'll be asked to link the particular repository that you have included your Docker file in, associated with maybe changing the path to the actual Docker file. You'll see that this is working by the fact that pushing a change to that repository will trigger automatically the creation of this container, which you should be able to verify. That is the end of the introductory course and prerequisites for the winter school. We have covered most of the philosophy and ideas around how we expect to work together in this winter school. We have told you a little bit about the services which will be running behind the scenes to make your life and our life easier. We've shown you and asked you to do some simple practical steps on getting your GitHub environment started so that we'll be able to collaborate effectively. We'll be using Docker quite heavily, and so we've asked you to create your Docker Hub account and make sure that you've done the simple steps of using Docker Engine on your laptop. And we'll be moving next into the more detailed applications, prerequisite applications for the rest of the school. Thanks.